Hello, my name is Nikos Petrelis, and this tutorial concerns the accelerated flow that can be followed for developing platforms that have accelerated operations. This means that some time-consuming operations or complicated operations are not executed in firmware, but using the reconfigurable hardware of the advanced Xilinx FPGAs. This is called the PL programmable logic part of an FPGA, while the host code runs on the PS part, the processing part of the FPGA, especially in ZCU102. There are 4 ARM A53 processors and 2 real-time processors that can be used for executing pure software. So you can see here 2 different paths that we can follow. The first one on the left starts from the officially offered platform for ZCU102, which is an XSA file. This is the file that is generated by the Vivado tool on the right. If we want to develop a customized hardware design. In this tutorial, we will only use the available platform. Maybe in another tutorial, we will also examine the customized ZCU hardware design provided by Vivado. After having available this XSA file, Petalinux operating system has to be built. All the accelerated applications do require Petalinux operating system, as well as Xilinx real-time, which is called XRT. In order to build the Petalinux project, first of all, we have to create a project. Here you will see the, without many details, the steps that have to be followed in order to build a Petalinux operating system. After creating it, we either have to determine using Petalinux config the hardware description that is available from the official Xilinx ZCU102 platform on the left, or from the customized XSA that has been developed using Vivado. You can see the different declarations that we have to make in either case. Afterwards, we have to run again Petalinux config in order to configure the root file system as well as the kernel. All of these are as well as the following step, which is the build of the Petalinux operating system. And if we have not already available the SDK, we have also to build it with the last scripts, Petalinux build --SDK and then /SDK.sh. But before, I have to say that some of these operations are quite slow, so when a slow configuration or build operation concerning the Petalinux starts, I will pause the video and resume after this step is finished. In the case we had used the customized hardware design provided by Vivado, we would also have to develop a platform project in Vitis. But if we use the left path, the available XSA file from Xilinx, then we can avoid developing a separate new platform project and go directly to the development of the application project. The application project can be verified in 3 alternative flows. Either in software or hardware emulation, or by deploying the application in real hardware. In this first tutorial, we will see only how we can emulate in software or in hardware the developed application, and how we can start such debugging. So, first of all, starting with a terminal, we have to source some scripts required by Vitis, XRT, as well as Petalinux, and a useful environmental variable called library path also has to be built in general for most of the applications that we're going to develop. So I have gathered all these script executions in one file so that I can easily run sources. The second name sources is the name of the script file. And then I cd to the directory where I will build all my projects. This is in my workspace. Then I go to the ZCU102 apps, okay, and then in ZCU102 min package, min comes from the word minimum requirements because it will be a very simple project. Inside there I have built from previous experiments a Vivado project, but we are not going to use this one. We will start directly by building the Petalinux project. As we saw here, we will gonna follow some instructions that I have on my file on the back. So I go directly to the steps for building Petalinux project. First of all, if we are not sure if Petalinux has all the dependencies installed, we can run this long instruction of 4 lines on the top. My Petalinux has been built correctly, so I don't have to run this one again. I will prepare some directories that I'm going to use in this tutorial. Well, here I am gonna make DFM, DFM, go inside DFM, and then build 2 directories, workspace 1 and another directory called boot. Workspace 1 will be used to hold the application project that I'm going to develop in Vitis, while boot directory will be used in order to gather all the necessary images produced from Petalinux build. I go to the parent directory where all my projects reside and start to create a Petalinux project. Following initially these steps, I copy this instruction. Of course, you can pause the video and see the exact instructions that I'm using. Creating does not take too long. A directory has been built. This is called ZCU102_min. That was the name I gave to my new project here. And in the template, I asked the Zinc multiprocessing course. So I'm jumping within the root directory of my Petalinux project and then run. Instead of running this one here, which would use the XSA produced by Vivado, I'm gonna use the full path of this is where the XSA offered by Xilinx has been stored in my computer. So I return again here, okay, and I have to run Petalinux config get hardware description equal to the path that I just copied. Let's see if I have copied correct. Something is missing. Okay, it's not a problem, it's my common mistake. What is required here is not the name of the XSA, but just the path where the XSA exists. Of course, there has to be only one XSA in a specific path in order to avoid the confusion. So Petalinux config starts now. I think opening the initial dialog does not take too long, so I may not have to pause the video. Yes, it didn't take too long. So what do I have to do right now is first of all to go to this option DTG settings and kernel boot arguments and deactivate the automatical boot argument generation, and then go to user set boot kernel boot args in order to set the boot arguments manually. I copy this one here. Well, what exactly do these options mean? Early con concerns some debug messages that will be printed by printk instruction. Clock ignorant used, as the word says, is about the clocks of the platform that I'm not going to use. And of course, we do not want these clocks to cause any problem. And then we define the root file system to be in the RAM of the system. And we will, towards this direction, we will ask for the rootfs image to be built as init RAM fs. This is one of the several options that the root file system has to be can be built in Petalinux. So I press OK here, exit. I think I can exit this menu. Let me see. Yes, okay. Before I exit this initial configuration menu, I will also have to select, as I said earlier, the init RAM fs. Let's talk about a little bit with the rest of the options that I have. Init RAM fs assumes that the file system is stored in the RAM of the system, not in the storage media like the SD card. This is a successor of the init RD option, and there are some other common options, like for example ext4, which is used in the case we have the root file system stored in a secondary storage media like SD card, eMCC, SATA disk, or USB. So I leave init RAMFS for my emulation purposes and exit this menu. Okay, I think I can exit now and press yes to save. And then we have to move and modify some necessary files in order to prepare the acceleration platform within Petalinux project. I'm not sure if this configuration takes too long. I'll wait for a while, and if it does not end soon, I will pause the video and jump to the next steps. Okay, the first configuration has ended, so I can, according to my instructions, I have to jump in project spec directory, then within meta user directory, and then conf, and there I will find user root file system configuration, and below this line I'm going to declare some config options that are necessary for XRT, OpenCL, and other things used by the accelerated platform. So I paste these declarations here, escape, right quit, and then move to another file which concerns the device tree. this is in, again, meta user, recipes BSP, device tree, files, and here it is the system user DTSI, concerns the device tree structure, and basically not the whole device tree structure, but the additional nodes in the device tree that are inserted by the user. I delete everything here and copy these contents here. I paste them. Starts here. Right quit. And then I'm ready to move to the next steps by configuring either the root file system or the kernel. Let's do the configuration of the root file system, which is a fast process. Does not take long. -c root fs. Okay, started, and here I just go to the user packages, and these are the ones I just appended in my first file. Appear because I appended them in the first file. So I just select them by pressing yes in each box and exit. Okay, now I will do the configuration of the kernel, which takes quite a long in order to start and have the menu appearing. So I'm going to pause the video and come back again when the menu has appeared. Well, Petalinux config -c kernel has finished, and this menu here has appeared after about half an hour. And according to the instructions that can be found either in tutorials available in the internet or according to the instructions given by Xilinx, one good modification, one necessary modification that has to be done is to increase the size of the contiguous memory allocator from 256 megabytes to 1024 megabytes. This is because in some cases the buffers are too large in order to be stored in 256 megabytes. When I'm saying buffers, I mean the operands, the input arguments of the kernels, which are the accelerated operations that will be implemented in hardware, as well as the results that they produced and will be read back by the host code. However, according to the instructions, we should expect to find within the device driver menu and the generic options generic driver options, we should expect to find an option DMA contiguous memory allocation, but there is no such option here. So we will not change this size, but I have to say that if we would like to modify this contiguous memory buffer, we could do this within the DTSI file that we modified earlier by appending some declarations that would reserve some part of memory in order to be used for this purpose. So for the present, I do not do this modification. I go directly to device drivers and staging drivers sub-menu. Staging drivers, and try to find Xilinx APF accelerator driver. Here it is, yes to select it, go inside, yes again, and I can go back. And it is useful, although I'm not sure if it's necessary, to also go in the CPU power management and deactivate the sleep modes by pressing no here, and in the frequency scaling also no to the first option in order to deactivate them. Okay, I think we can exit this menu now, save the configuration, and then the following step is to Petalinux build, to execute Petalinux build. That will build the project and it will take some time, so I will have to pause the video for a while. Petalinux, may be better to return to the root directory of the project. Here it is, so I run Petalinux build and we wait. Okay, now that Petalinux build has finished successfully, we can move to the next steps, which concern the Sysroot. I have to say that if the Sysroot is already available, we do not have to follow these steps. But in my case, I recreated again, so I moved the images Linux directory, and within this I run Petalinux build --SDK. I think it also takes some time, so I will pause the video again. Well, Petalinux build --SDK has finished, and what has been created in this directory is a shell script file called sdk.sh, which can be run in order to create the sysroots directory. Although there is a sysroots directory available already in this computer, I will also make a different one under PFM directory that I created at the beginning. PFM exists, let me see, space ZCU. Okay, we want within this directory, within this folder, to create the Sysroot directory. This is the whole path. So I'll run .sdk.sh. It starts, and instead of overriding the existing one, which is in this directory here, I will install it in this directory. Proceed, yes, and we wait for a while until the SDK is installed. What we have to do next is, first of all, if we were following the path with the customized Vivado XSA file, we would also have to create a BIF file which shows how the image will be built if we want to copy this image to an SD card, for example. In our case, it is not necessary, so I will just copy the files that have been produced within the Linux directory here in the boot directory that I have created. In this one, sorry, pfm boot. which is empty for the present. Of course, I could also have used these files within the original directory here. These are all I need. I'm just copying it to the boot directory because it may be useful for other flows, like for example for real hardware deployment. Let's copy everything from here to this directory. And then I am okay, so there's something wrong here. I didn't notice that I had this message here. So, okay, I canceled the copy, and I will also rerun the this script here, because as you will see from my notes, the failure that I get is owed to the already defined things within the LD library path environmental variable. So in order to avoid this failure, I have to unset LD library path and then repeat this SDK creation. So I'm copying the previous path, which is this one here. I copied the dollar symbol. So it says that it already contains an SDK because it started doing things with this directory. But if I ask to proceed, the old files will be overwritten. So I press yes, and the clear SDK will be installed, I guess. We will see from the messages if there is a problem here. And then I will also copy again the files in the boot directory. Some things have been copied. I remove them. It's clear again, and copy them again. Okay, copy everything to this directory. I don't mind if it does not copy the subdirectory. I anyway do not need all the things that have been generated here. So the next path will be actually to skip the beef creation, and we will go to the I don't need this anymore, to the Vitis environment in order to create a new application project. Wait for a while for the copy to finish. Okay, it has finished. Everything is here. So I start, I go within the ZCU102 min package directory, and within PFM, and I will start this application within the directory workspace 1. This is empty for the present. I go to the parent directory and start Vitis, saying that the workspace will be WKSP1, and wait for the Vitis to start. I create an application project directly. It will be based on this platform from the repository, which is the official one. It is recognized. It is both targeted for embedded as well as acceleration flows. So I keep this one. You can see below some features, for example, which clocks are available for my peripherals and my kernels. The system project will be ZCU102 min app. And here is a critical point where maybe some of the options that I will declare here do not work, so be careful. In the Sysroot path, I will declare the one I have just created, and it's not just it does not stop this path here in Sysroot, but I have to select if I have ARM or Alveo cards with x86-64, which would in this case would select this one. But now for Zinc MP, which has ARM processors inside, I will use this one directory, and now I select OK. Concerning the root FS, I will have to go to the boot, or maybe from the original Linux directory that I had available as a source. And the one I have to declare, the one at least I have tested successfully, is this one here. There are plenty of rootfs directories in different compression formats, but this rootfs star gz works in my case. So I select it. And concerning the kernel image, the correct kernel image is this directory here. Is this file here, I'm sorry. Okay, so I proceed. And I select a template application, vector addition, for example, which is the only one for acceleration templates. Finish. And here it is, it has been created. The default flow is software emulation, and we will start from this here. You will see the options that both host and kernel debug is supported. Although kernel may be tricky in some cases, and if I assume that the kernel is anyway correct, I may debug only the host part, the host source code. However, my purpose is not to do the full debugging here of this application, just to see the environment and how we reach the debug process. Right-click on emulation software and build this project. It will take some time, so I will pause for a while the video. Okay, the build has ended. It didn't take so long, just 1.5 minutes, and it completed well. We don't see any error message here, so we can proceed with the debugging. We use debug and launch on emulator as a single application debug. I start emulator and debug. On the bottom right, we will see what happens with Petalinux, which will be loaded on the QEMU emulator, while in the main frame will appear the main host code of my project. Petalinux is building. It will take for a while until it will proceed after this point. everything will be emulated in software, in this case. We're at the point where U-boot script has started, which will take the process of booting the main kernel image. Okay, the kernel image has been loaded and it continues booting. And we will see the prompt for login in a while. We're still waiting. Okay, I think at this point, here it is. We will get the prompt to login, although this is not necessary because the host code will also start being debugged. You can see that I get the login here, but I will also get the breakpoint that the control has stopped to the first command within the main of the host code of this application. So whether I root login here, root, I have logged in. I don't see anything, but if I go to the mount directory and within sd mmc block 0p1, okay, here you will see that we can find everything concerning the files that we would need to run our application. Here is our executable, here it is, and here it is the binary container XCL bin, which holds the description of the kernel. However, we will focus here on the debugging environment. We can see that from here we can step and in parallel observe the values of the various variables and parameters. I can also see the value of the parameters by placing the cursor over this, etc. Of course, my target is not to debug the specific application, which I have to admit that in some cases may fail to execute as expected, but this is out of the scope of this video. So what I'm going to do is to stop the debugging and return to the design view and build the emulation hardware flow, which is the second one we will see in this video. Let's build this one here. Since it will take longer than the software build because the hardware is emulated in a machine level accurate simulation, it is more detailed, and as you will see, we will emulate the hardware using the Vivado that will appear when we start debugging. For the present, I'm pausing for a while the video until the build stops. Okay, hardware emulation has been built also successfully, as we can see here. So we proceed with debugging. Restart emulator, because the previous software emulation was still active. Okay, QEmulator is also starting again on the right, but as you will see right now, what's different from software emulation is that directly Vivado pops up in order to emulate my hardware component. I don't do anything, it automatically opens up these windows, and actually what is going to show me is the waveform editor, which shows some master axis buses and what kind of data transfers will be put here. So it asks me from Vivado simulation to invoke run all from run menu. Run menu, run all. So it starts operating here, and I will return back to my Vitis environment and watch what happens with emulator, because Vivado will be simulating the hardware, Vitis will be simulating the software. I expect from this console the QEMU process to proceed. Until it does so, we can have a look at the Vivado, where occasionally some data transfers appear. Here you are, and let's see if we have anything proceeding in the QEMU. QEMU loads more, boots more slowly in this case, because it interacts with the hardware emulation. Let's go back. It's about 600 microseconds. The simulation has proceeded up to this point. Still in the QEMU process, it takes quite a long at this point. This was also a point where we had stuck for a while, even in the software emulation, but now okay, we see that the and emulation proceeds. This is actually a co-simulation between hardware and software, because even for this part of the operating system boot, the hardware emulates the Vivado, let's say, emulates the behavior of the real hardware during the boot process. We're at about a little more than 1 millisecond has been reached. We still have not reached the login. We're still waiting. The simulation in Vivado is about 1.8 milliseconds. I think at this point the login prompt will appear. Okay. Here it is. So I may log in. And as you see, again, the control has stopped at the beginning of the main function. Let's see what happens in Vivado. if it's still proceeding its emulation. There is no reason why it should not proceed with the emulation, since there is an operating system running underneath the application, and we simply are interested to focus on what happens here, and we can again proceed with stepping over or stepping into instructions, and by watching the local variables changing and things like this. So as I said earlier, debugging is not debugging of this specific application is not the purpose of this video. We will end here, and please be aware of the following videos that will be released showing the real deployment, the deployment of the application in real hardware, as well as other aspects for beginners concerning Vitis and accelerated flow. Thank you for your attention.